We're now going to take a look at the concept of the domain of a function of several variables. And the domain is something that we are used to. We know what the domain is in concept, and for many functions of one variable, we're actually able to compute the domain. And it turns out that this concept is easily extended to functions of two or more independent variables. We just need to take a look at some examples, and then there are a few ideas that are more prominent when you go to functions of two or more variables than, say, your basic functions that you'd have started with in let's say a college algebra or a pre-calculus course, right? So let's start with the functions of this form, right? And remember, this notation is saying that we're working with functions of two variables. So essentially, these are functions that depend on, let's say, an x and y, and then the output would be a real number. So the domain, right, of f is the set of ordered pairs, right? And again, we'll just say x and y. We're just using our standard variables. So the domain of functions of this form is a set of ordered pairs x, y such that f of x, y is well defined. For without oversimplifying, what it basically means is, now can we identify all the ordered pairs that we can evaluate in this function and get a real number, right? So in some functions, it might be all ordered pairs. So every value for x and y, right, is allowed. But in other functions, there might be restrictions on x or restrictions on y or both. And what we're going to be looking at now are some examples where we determine, what's the case, and then possibly even like sketch the domain, because when you can visualize something, it really does help. All right, so let's start with a simple example. So let f of xy be the function x squared plus the square root of y, right? So let's ask ourselves this question, right? For what values of x and y is this function well defined, right? Well, now this is a simple function. It only has two terms, and it's like the x and y are separated. So, this term only depends on the x value. This term only depends on the y value, and you're adding together, right? So we know that nothing can go wrong with addition, in the sense that if this term gives me something real and this term gives me something real, then I know I can always add them together, right? Now let's think about the x squared. Well, really, this term can always be evaluated. This term is always well defined, right? So this term alone is defined for all real values of x. This term, the square root, is a little bit different, right? If you're taking the square root of y, well, the only way this term will be well defined is if y is something greater than or equal to 0, right? If you're working only with real numbers, and that's what we're doing, right? This term here is defined for y greater than or equal to 0, right? So in fact, the domain of this function is not the entire plane. It's not all of R2. It's really just a subset of R2. So based on this observation, we could say that the domain of f. Now you could say f, or if you want to, you can specifically write this notation. It means the same thing. This is just a little bit more explicit in the sense that it's telling you what your independent variables are. But the domain of this function, let's write it in the set builder form. So the domain of f of x, y it's a set. And what is it? It's a set of all ordered pairs, right? And then when you're using that set builder notation, you describe, okay, it's an element of these types of sets. I'm sure it's a set of these types of elements. And then you state any restriction or any conditions that x and y must satisfy. Well, we know that x really, there are no restrictions on x. Commas in this context are interpreted as an and, so x can be any real number and your y has to be greater than or equal to 0, right? You could certainly write it like this. If, however, you see something like this, it's interpreted to be equal. So if you say that you're stating a set of ordered pairs and you only state that y is greater than or equal to 0, then this condition is implied. So essentially in the set builder notation, the only things that you have to state for sure, like after the colon, or sometimes you'll see a vertical line, but when you're describing what conditions must be satisfied, if there are no conditions on a particular variable, you are allowed to leave it out. So that's why I'm saying that these two sets are the same. All right. So yeah, so that wasn't too difficult in terms of coming up with what that set is. Now, an important skill is the ability to sketch this set, right? Just like how when you work with, let's say, inequalities or even domain, when you have a function of just one variable and you might have to sketch your answer on a number line. Well, you sketched your number on the number line because back then it was a subset of the real line, right? Now this is a subset of the R2, the set of all ordered pairs. So let's say this domain may be sketched as follows. All right. So what do we do? Well, I am going to sketch my XY plane. Right. And then let's see what it says. Now, there is no restriction on X, right? But there is a restriction on your Y value. It says that your Y can only take on non-negative values, right? So 0 or greater. Well, in the XY plane, think about this. The line Y equals 0 is the x-axis, right? Right. So the domain can consist of all the numbers on your x-axis, right, with both of these two combined, and all the points that are above the x-axis. So basically, it's all the points, including the x-axis, that are in the first and second quadrants. So if I wanted to sketch this so I can visualize, it would be something like this, all of that. And just for emphasis, since I'm using a different color, I'll include this line as well. All right. And this would be the sketch of this domain. So what this is basically saying, you can pick any ordered pair in the blue, and when you attempt to evaluate the function at that point, right, then you will always get a real number for your answer. So you'll never get something that's undefined. Everything will be well defined. The flip side is if you pick a point down here, so if you pick a point anywhere on the negative y-axis specifically, or in fact anywhere in the third and fourth quadrants of your xy plane, then yeah, this function will not return a real number, right? Yep. There you go. We can describe the domain symbolically, and we can also describe it graphically. Now, just some other terminologies. So this line here, right? This line is almost like a fence. And it basically says, as far as the domain is concerned, thou shalt not go below this line, right? So everything above the line is fair game. Everything below the line is fair game. Now, the points that are strictly above the the line, this, as far as the set is concerned, this part here, right, strictly above the line, this is called the interior of the domain, right? These are all the points inside the domain. This line, again, it's almost like a demarcation line. This line that kind of says, okay, this is as far as you can go. You can't go any further. Where if you go just a little bit above, you're inside. Well, if you go just a little bit below, we now refer to this as the exterior of the set, right? And then, so what about the line itself? Well, the line itself is called the boundary of this set. So this is the boundary, right? So, I mean, I guess more precisely, I should say this is the interior of the domain, right? All the points that are strictly where your y is definitely greater than 0. All the points where the y value is less than 0, this is the exterior of the domain. And then that line that kind of straddles both. Like, again, see what happens is on the boundary, like if I were to draw a circle anywhere on this boundary, I would contain that circle would include, or the interior, or the inside of the circle would contain some points that are interior points and some points that are exterior points. It's really that line of demarcation, and this is described as the boundary of the domain, right? Now, the idea of interior, exterior, boundary, it's not specific just to domain. You could describe sets, right, in terms of, well, I should say characteristics of these sets without talking about the domain. But in our context here, these ideas will come up. Now, um, if a region, or, well, yes, let me just say this. If a region, and actually this is not just in the xy plane, so just in general, if a region does not contain any of its boundary points, right, the region is said to be open, right? So the region is said to be an open region, right? If a region contains all of its boundary points, then it's said to be closed, right? So if a region contains all of its boundary points, right, the region is said to be closed. Right? But you can't think of these two properties as being opposites, because you have some regions, and we'll see it here in a second with a few more examples. You'll have some regions where some of the boundary points are included and then some aren't. So I'll just say there are regions that are neither open nor closed. So you cannot think of these as opposites, right? So here's another example. Suppose I have this function. Again, this is another function from R2 to R, and let's say it looks like this. It is the square root of x, and then let's say plus the log of, sorry, the square root of y plus the log of x. Again, I'm keeping it fairly simple just to illustrate these concepts. Well, here's what we know about the square root function. I mean, we just said it earlier that this implies that y has to be greater than or equal to 0. Well, for the natural log, in addition to not being able to take the natural log of a negative number and get a real number as your answer, we can't take the natural log of 0. So the inequality is a little bit different, right? Guess I'll go ahead and do this, right? This term implies that x has to be strictly greater than 0, right? So let's see if we can. So as far as the set notation, this is what it would be: a set of all ordered pairs. Now we have restrictions on both, so we have to state both, right? It doesn't matter if you do them alphabetically or reverse alphabetically. You could just say, yep, your y has to be greater than or equal to 0, and x has to be strictly greater than 0, right? So now let's look at the sketch and see if we can identify the boundaries, interior, exterior, and then determine if this set is open, closed, or neither, right? Well, in fact, the boundaries are actually easy to sketch. So the line y equals 0, right, where we have the equal sign there, that again is our x-axis. So I'm going to draw that with a solid line like this, right? So that's the line y equals 0. Now, the line x equals 0 would be your y-axis, but notice we don't have an equal sign on this inequality. This is what we call a strict inequality. This is a non-strict inequality. So if I were to sketch this, the convention is any boundary, right? Any boundary where it's defined by a strict inequality, where it's not included in the set, then you have to draw it as a dotted line, right? So this is the vertical line, right? X equals 0. Let me make that a little bit more pronounced. There we go. So, yeah, so this is the line x equals 0, but it's not included because this is saying that x has to be strictly greater than 0. So we use dotted lines for boundaries that are not included, and then solid lines for boundaries that are. And in fact, there would be a hole here at the origin, right? Because since x has to be strictly greater than now, that would be everything to the left, I'm sorry, to the right of this vertical line. And because then y has to be greater than or equal to 0, it could be any point on the horizontal line and above. So when I put all those things together, this will be my sketch, right? It's all points in the first quadrant and along the ray. Remember, this could be described as a ray, starting at the origin and going in the positive x direction, right? So there you go. This is our domain. I could take any ordered pair in the first quadrant, plug it into this function, and I'll get a nice number. It could also be along the positive x-axis. That would work, but I can't pick any points over here or here or here. So let's write this. So right here is the not exterior, this is the interior, right? So these are all the points in the set. So this is the interior. Everything out here is the, I'll kind of write like this, the exterior going all the way around here. So these are all the points that are outside. Now, this region that we've just sketched, it has two boundaries. It has the positive y-axis as a boundary and the positive x-axis as a boundary. The points along the x-axis, the positive x-axis, those points are included, but not the points on the positive y. So because of this region, it contains some of its boundary points, but not all, right? So because of that, so in fact, let me highlight so this, there's our boundary, right? So since some of the points are not included because of this inequality, but others are because of this inequality, then we would say that this region is neither open nor closed, right? So this domain, in fact, let me just write it over here. This set is neither open nor closed. All right. Now, let me do another example, and then we'll use this to illustrate another property that's often associated with these types of regions/domains in the XY plane. Right. So let's look at another example here. So let's say we have this function. Let's say we have arc sine of x plus arc cosine, let's say y over 2. So let's do it like that, right? So now we have some inverse trig functions, and let's see what we can determine based on, properties. What do we know about these inverse trig functions? Well, it turns out they share similar properties. For the arc sine to be well defined, then your x, right, the thing that we call this the argument of the function. So the thing that you're sort of taking the arc sine of, that thing has to be between plus or minus 1, right? So in other words, the domain of your arc sine function, your basic arc sine function, is saying it's where your x has to strictly be between plus or minus 1. This one, it's very similar, actually. And for arc cosine, your argument, whatever is the inner function in your arc cosine function, has to be between plus or minus 1. Multiply this inequality by 2. So then this tells me that my y has to be strictly between plus or minus 2. So here is the domain, right? So our domain here, as usual, I'll start by writing it as a set, and it is all values of x between plus or minus 1 and all values of y between plus or minus 2. And let's see if we can sketch this. Now, this is, so if we think about like how many boundaries are there, well, technically there are 4 boundaries, right? Because there are 2 bounds on the x and then 2 bounds on the y. So let's sketch them. In fact, okay, so let me go ahead and draw the x and y axes. Let's start with the x. If I ask to sketch the line x equals -1, well, if you're sketching that sort of line in R2, that's going to be a vertical line. So it's going to be roughly here. And this one I'm drawing solid because we have the equal sign. In fact, all of these lines that I'm about to draw are going to be solid because this is saying that the endpoint is included. The endpoint here is now this vertical line. And then when I look at the line x equals 1, it's similar. It's that vertical line. There we go. Now, when we look at the restrictions on y, so if we look at the boundary that's based on the lower bound here, that would be y equals -2. And again, it's included, so it's somewhere down here. I'll just label it. So y equals -2 is that horizontal line. And then obviously the last one would be this horizontal line, y equals 2, right? And so now, where would we shade? Like if we wanted to shade the domain, well, it would be everything between x equals ±1 and between y equals ±2. So it's essentially this rectangle right here. So this will be the domain. So in order for me to evaluate this particular function, I can only pick ordered pairs inside or on this rectangular region, right? So again, let's highlight the so this would be the interior where I've shaded. Now, because the all of these are boundaries. So this region has 4 boundaries, 2 horizontal lines, 2 vertical lines. So let me see. Well, let me write it out here. So the exterior is everything around here. So I'll just see what's the best way to do. Yeah, so I'll just say exterior, 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 oh, exterior. So everything that's not shaded, you know, is considered the exterior. And then of course the boundary is now consists of these 4 lines. So let me do it like that. Just kind of highlight this. And again, I'm doing it as a solid line because it is included. So that green rectangular boundary, right? That is in fact the boundary of the region, right? And since the entire boundary is included, then this domain is closed. So this is a closed region in R2, right? So it's kind of it's an interesting concept in terms of being able to identify these particular properties. Now take a look at this domain versus this domain. If you notice, in this domain, there is no restriction on how big your y can be or your x can be. So you can go as far to the right or north as long as you stay in the first quadrant. You're good to go. Whereas this region right here is actually, there is a bound. There's a bound on how big your x can be and how, y can be and how small y can be. And similarly, a bound on how small your x can be and y will be. This type of region, right, is described as a bounded region, right? So I'll just say, moreover, this domain or this region, I'll just say this region is a bounded region, right? Because there's a limit on which or a limit for both your variables. So this one is a bounded region. And this one up here is unbounded, right? So this one is unbounded because there is no upper limit on your x, and also upper limit on your x going in this direction. You can go as far here to the right, or you can go as far up as you'd like, right? And that makes it unbounded. And we're going to be referring to these words as we go along, but it's kind of a good place to introduce this, because we are talking about sets, right? It's a set of ordered pairs, and what conditions do they satisfy. And when you look at what region, or what sort of, sometimes this is referred to as the feasible domain or the feasible region. When you look at it, you can be asked to answer these questions about open, closed, identify the interior, exterior, what's the boundary, is the region unbounded and bounded. So from a visual standpoint, it's usually fairly straightforward to see. But the key is, and this is kind of why I went through and I did several different types of, basic functions that you have to be able to recognize, that all of these questions begin with understanding properties of our functions, right? So whether it's our, algebraic functions like a root, or our transcendental functions like ln and inverse sine, inverse cosine, we have to know those properties before we can even think about, describing the set as well as sketching the set, right? So good little review of some of these algebraic and geometric concepts, but now again in a slightly different context, albeit still just about functions, right? See you in the next video.